great honor to be here and present this for you. Talk a little bit about our group work. And we work at UFMG, Chemistry Department. And I heard that you didn't have time to visit a little bit our university yet. So you can see that we have some nice landscapes, and I hope you can come back. And also to visit our microscopy center. That's a new facility that just is being improved, and we have nice equipments to show. So I would like to invite you to come back. So this is our group at Chemistry Department, and we work with polymer composites. And our goal mainly is to really think about everyday applications and think about the new materials. So polymer and nanocomposites can go and have applications in the technological necessities from Brazil, from the global market, for example, in the case of oil and gas industry. So this is the people working with us in the chemistry department. Some of them are here. And we have many collaborators here with ongoing work in the physics department and also with Professor Ijima at Rice University in the United States. So this is our system. It's the polymer in contact with, in the interface with carbon nanotubes or graphene. And this is not an easy system because this interface does not like each other very well. So the interface are slippery, and to really make them compatible and can get some nice properties from these materials, we can work very hard in the chemistry at this interface. So I will give 2 examples of very recent works. We just finished, this work is just being published now. And it's a collaboration with Professor Ijima and our group in UFMG. It's about a thermoplastic polyurethane. This is a kind of specialty polymer, which has some very specific applications with, when we need high performance, like abrasion, like resistance to temperatures, to solvents, and the carbon nanotubes can give new open horizon for this material. So Professor Ijima had shown that the impregnation, the infiltration of PDMS, another kind of polymer, make it possible to do composites in oriented or random structure that are very different in properties. So we try to use this approach with our polyurethane experience. And polyurethane is a material that has phase-separated structure, and the cross-linking is through hard segments organization. So this is a quite flexible material to allow us to explore some new properties. The glass transition and melting of these domains, like hard domains or soft domains, will control the range of working temperature for this kind of composites. So we infiltrate nanotubes, carbon nanotubes, long and aligned carpets of carbon nanotubes, and also to comparison, we prepare random composites by the coagulation method. This kind of small block, which has 1 centimeter more or less inside, was characterized for several techniques. Here we can show the morphology where the carbon nanotubes are very well dispersed, but also have some wave structure that allow us to show, for example, in relation to mechanical properties measured by DMA, dynamic mechanical analysis, an improvement of 1 order of magnitude. This was measured in 3pK in a storage models. We demonstrated 1 order of magnitude increase above room temperature in this kind of mechanical characteristics. Also, class transition increased, and it depends of the kind of nanotube orientation. But in summary, we have for the oriented material with a high aspect ratio nanotube, an increase of 1000% in reinforcement, which shows that this kind of material can really give some new open market for the polyurethane, thermoplastic polyurethane. Also, the conductivity is very different between the two kinds of materials. This is correlated to the orientation and also the aspect ratio. Another example I want to show you is based on nanocomposites from epoxy. This is a result that we just get a few weeks, last week. And what we are doing is that we have this kind of graphene oxide from National Geographic. We use their sample called expanded graphite. This is a very important sample in relation to the Brazilian possibilities as graphite production. And we did some typical chemical methods for exfoliation and also functionalization, but with a special kind of function, which is a 3-ethylene tetramine, theta, that is a function that can be very useful for the incorporation in the epoxy in relation to this interface carbon nanotube epoxy. So the same thing was done with multi-wall carbon nanotube, the synthesis of functionalized by theta carbon and multi-wall carbon nanotubes, and the preparation is a commercial type but dedicated for nanocomposites in a commercial 2-wall mill, 3-wall mill equipment was used, but with some kind of special conditions to really allow dispersion and distribution of a nano reinforcement inside the polymer. And with this kind of preparation now, from thermomechanical analysis, we could show increasing glass transition, which this property is is really what they ask us to improve from our pattern of our company that asked us to change this epoxy. So glass transition is our goal, and we have improved in all conditions, but we can see, for example, that with multi-wall, we have a very nice improvement of almost 30 degrees Celsius, which really allows us to use this epoxy in conditions, very harsh conditions for the material. So this is some images that show how the dispersion is and how the connection between tubes. And so to conclude, I want to say that this is our approach. We are working in chemistry of materials and looking for opportunities of new technologies, new demands for materials in the industry close to us. And these are people that are financing us. And I'd like to thank you very much for this opportunity.
I wonder if you study the percolation properties, which concentration would it percolate? If it is possible also in this aligned to percolate.
As this is an aligned but wave material, so there is connection between tubes in the two directions.
Okay.
So the percolation for this material was not our goal. We have another studies with percolation. It depends of the aspect ratio of carbon nanotubes, But in general, percolation for these unidimensional materials is in very low concentrations, like below 0.1 weight percent, for example. But percolation is not the problem. The problem is the level of conductivity after percolation. That if the material is not really perfect and the aspect ratio, how level of conductivity you can get inside a composite. 10 minus 2, 10 minus 4, 10 minus 1 Siemens by centimeter. This is the main problem.